In part 3, we were asked to find precise answers to the questions we have already solved with the average velocity table and estimates. So we're looking at the same thing, but we're just finding precise calculations. So the thing for us to remember, of course, is that we have two dimensions. So we are going to set up a system of equations for each dimension. So in our x dimension, we have our Vx equals at plus v0, and our x equals 1 half at squared plus v0t plus x0. So Vx, the instantaneous velocity of x at any moment in time, is equal to the acceleration times the time. Well, horizontally, there's no acceleration, so that term drops out. And the initial velocity, in this case, we'll start with our using our 700 meters per second. We have Vx equals 700. And so this model that describes the velocity at every moment in time says that the velocity is 700. It doesn't depend on the time. That's what this equation says to us. So now we go to the x, and 1 half at squared. Again, the acceleration is 0. The initial velocity is 700, so we have 700t. And if we set the initial position equal to 0 horizontally, this is 0. So our instantaneous position is given as 700t. So these are the two models that we would use to describe the motion in the x direction. Now moving on to the z, Vz equals at plus v0. It is accelerating in the vertical direction, so we have minus 10t, and the initial velocity in the vertical is 0. So we have Vz is minus 10t. Now for z, 1 half at squared plus v0t plus z0. The instantaneous vertical position is 1 half times minus 10. The initial velocity in the vertical is 0. And if we set the initial position equal to 0, that's also 0. So we're left with z equals minus 5t squared. And so these are our models that will give us the instantaneous velocity and position in the vertical at any time. So we want to know when this thing hits the ground. Well, in our picture, we know we have this thing that is 8 meters. So we have 0 and minus 8, and the bullet is fired, and it hits the ground some distance away. We've got minus 8 meters. So we want to know when the bullet is at the ground. So this is the position of the bullet. The position of the ground is minus 8. And we want to know where those two meet each other, where they intersect. And so that is when minus 8 is minus 5t squared. So t squared then is the square root of 8/5. And that is 1.2649. Now in this problem we have, if it's 8.0 meters, we have two significant digits we could use. So the time is about 1.3 seconds. Now if we go back and check our average velocity table, we'll see we expected it to be just a little bit over 1 second. So that's consistent. So now we are going to take that value. Oh, so how far will it land from the base of the platform? Well, how far? That's horizontal. That goes over here. So now we substitute in over here, and we have x equals 700 times 1.2649. And again, we use the unrounded number because we never round until the end, lest we propagate the error even further. And so that gives us 885.43 meters. And in this case, we really should only be reporting two significant digits. So we would say that then we would have, it's about 890 So that would be 8.9 times 10 to the second meters. That's how far it goes horizontally. And again, we wouldn't report 890 because we would be suggesting there are three significant digits, which there aren't. So the way we solve that is to write it in scientific notation. So how far will it land from the base? What are the vertical and horizontal components of the bullet's velocity? Well, we know the horizontal is 700. It remains the same. So now we take that number and plug it in here. Vz is minus 10 times 1.2649. And that's then going to give us minus 12.649 meters per second. Into two significant digits, that's going to be minus 13 meters per second. Vertical, horizontal components. The magnitude of the impact velocity. Well, in this case, we have a 700, and we have a minus 12.649. And this is our impact velocity. And so that impact velocity from the prior solutions of the Pythagorean theorem is going to be the square root of 700 squared plus 12.649 squared. And some of you may wonder, why do I drop the negative? Well, that's because if I square a negative, I still end up with a positive. So in other words, it doesn't matter whether this is positive or negative, we will end up with the same answer. And so we're looking at the square root of 700 squared. We might expect, because 700 is so large compared to the other value, that the other value may not have any noticeable effect given the uncertainty in the measurement. So 700 squared plus 12.649 squared is 700.1 meters per second. And so if this has three significant digits, we can still only report 700 meters per second. And if you recall, we did this with our estimated values and we got the same answer. But just to be true to ourselves, we'll calculate the last question is, what is the angle? Tangent theta is opposite over adjacent. And tangent theta in this case is 12.649 over 700. And so theta is the inverse tangent of 12.649 over 700. And that is 1.035 degrees. 1.035 degrees. Two significant digits is 1.0 degrees. And that would be the impact angle. So that means during this time, it will only have dropped 1 degree. That's the angle of that triangle. And that is how we find the analytic solutions.